Okay, I'll start. So we'll now have a talk about the Poseidon Pipeline for Ocean Features Detection with Sentinel-2 by Emanuel Castanho and Andrea Giusti from the AirCentre. Emanuel holds a master's degree in aeronautical engineering from the University of Beira Interior in Portugal. Currently, he works at the EO Lab from the AirCentre as a project developer in projects of national and European scope. His specialization is Earth observation data applications across open science domains, with a special focus on advanced machine learning techniques applied to satellite optical data to detect marine pollution. He is also involved in operation phases of new satellite missions, including use case definition according to stakeholder needs. Andrea is a project developer in the AirCentre, supporting the execution of technical activities of the Earth Observation Lab, related to the analysis of remote sensing data, design of geospatial workflows, including results dissemination and outreach activities. He holds a master's degree in environmental engineering from the University of Bologna, and previously he collaborated within the United Nations Satellite Center as a geographic information systems analyst. Thank you very much.
Okay, so thank you to everybody. So today's session, me and Emmanuel, we will give you a presentation about Poseidon, which is a tool that we have been working in the last year, let's say, and is a pipeline for the detection of ocean features with satellite Earth observation, and in particular with Sentinel-2 data. As you may know, many features are present on the ocean surface, and especially the one that can be observed by satellite. Today's presentation, we are going to focus on the problem of marine pollution, and more specifically on what can be called in a larger way as marine debris. I think we are all familiar kind of with what we are talking about. So marine debris is basically let's say an umbrella term that includes, let's say, an enduring manufactured processed solid material that is discarded, disposed, and then abandoned and can end up in the marine environment or in coastal environment as well, of course. So as you can see, plastic is of course included into this large term. And as it represents nowadays one of our greatest pollution problem, we decided to try and develop something that could be helpful for this cause, and was one of our, let's say, motivation for developing this tool. So in addition to common plastic items, it's also quite typical to come across other type of plastic in this kind of, let's say, bunch of material called marine debris, such as fishing gears, rope, nets, and wood, and many more. And because of this complex and diverse nature of the problem, and different, like, somehow shapes and sizes that this material can appear on the ocean surface, for example, it can appear in large accumulation. Somehow, like this can create like a threat not only to the environment, but also to the navigational system and safety, to the economy, and of course to the human health. So there are different ways that how it can interact, it can enter the ocean. It can be from different sources and for different reasons. For example, it can enter the ocean in the aftermath of huge flooding events and catastrophes. For example, in the aftermath of a hurricane landfall, here we picture the example of Acapulco, Hurricane Otis that struck Mexico coast on October last year. And like, as you can see, many material was transported by the floods to the ocean and then washed ashore. But also other type of way that can enter in the ocean, like, for example, spillage from say vessel that like somehow lose like containers or material they are transporting. And this is an example that happened in Spain exactly a month ago, and create a big, of course, environmental emergency and issue in the coast of Galicia and so north of Spain. So for the motivation for working on this issue and developing our tool is that Sentinel-2 has been proven by recent studies, both in real cases, but also in control experiments, to have a really great potential to detect accumulation of floating marine debris, even though it originally was not a sensor like satellite designed specifically for ocean application. And the reason why, let's say, it has a great potential is because, of course, it's free of charge. It provides a good trade between spatial resolution with bands having from 10, 20, and 60 meters of ground sampling distance, and revisit frequency of up to 5 days for most of the coastal waters. Has, of course, a kind of global coverage, as I said, like in coastal waters. And the multispectral instrument, it covers wavelengths of visible, shortwave, infrared, but especially in the near infrared, which is particularly helpful and suitable for detecting and differentiating small floating objects on the ocean surface. Of course, like let's say this technology is still like in an early phase of an evolution for such a purpose. It holds a lot of promises. That because satellite can somehow keep an eye on much bigger areas, even like those areas that are really hard to reach, so off the coast, for example, and especially the ones that are not reachable by on-site observation. It helps to fill the gaps, as I said, also where we don't have so many on-site observation, gives us a constant, regular, and long-term data, which helps to manage and foster somehow cleanup activities of marine debris. It supports effective monitoring, of course, for management and remediation policies, and is a cost-effective and replicable solution. So how, let's say, marine debris it looks in pictures, so in satellite picture and Sentinel-2 pictures. Well, as you can see in this example in the Gulf of Honduras, marine debris pixels are appearing as a very bright features. In this case, it's a filament that was spotted off the coast of Honduras in the aftermath of the transport of a large amount of debris from Honduras, and that originated in Guatemala, and that was spotted like kind of near the coast of Honduras in this case, and near to an archipelago which is near to the coast. But also, as you can see here in the top picture, these satellite images that were taken from controlled experiments where they deployed some plastic targets on sea, and they acquired some satellite images. Also here, as you can see in the top right picture, you can see that this material appears as a bright feature. But as you can imagine, you have illustrated here, this is not the only bright and especially not the only floating material that appears on the ocean surface. So here we have some example of natural origin, such as macro and microalgae, cyanobacteria, seas knot, jellyfishes, and sea pumice that can originate from underwater volcanic eruption. Also not such a common thing, maybe shrimp's eggs and tree pollen. But also, so you have here like pictures, some other things that it's possible to see, which maybe is more common. Of course, water, but also sediment-rich water, vessels, offshore structures, and all the features that also are related to the ocean surface and are always there. And as you might saw today, the waves here are creating a lot of white caps and sea foam sometimes that for us is creating a bit of challenges, especially in the differentiation between marine debris and these kind of features. Of course, we have clouds. Of course, they are not floating, but they are always there. As you could see, there are several types of objects that to take into account in the detection of ocean features using satellite. Fortunately, there are some really nice initiatives. This one's called MARIDA, Marine Debris Archive, that has overcome some of the challenges that we are facing in our objective. So this is a spectral library dataset that with annotation derived from a verified debris event together with several other ocean features in multispectral data collected by Sentinel-2. The annotation are around 800,000 and are divided in 15 classes that range from plastic, natural organic material, vessels, the wakes of the vessels, foam, clouds, but also different type of waters, because it's not just clear water, but turbid water, sediment-laden water, and shallow water. So thanks to this open access dataset was another great motivation for us to develop such a tool. And this dataset allows us to explore the spectral behavior of the specific floating materials. And yeah, was one of the things that driven us to create a remote sensing and machine learning pipeline such as Poseidon. To determine the different type of object present in the image and finally to obtain our final results, so to classify it. We use these different spectral signature provided by MARIDA, but also some that we extracted ourselves. And we used to compare the reflectances of objects in a subtle image to the spectral profiles of materials that we already know. For example, here you have some explanation about how it's possible to see the difference between ocean water, floating plastic, and vegetation, especially in the near-infrared part, while the water has a pretty low reflectance, but floating plastic has a high reflectance, but have still a flat spectrum. And instead, like in this case, is dense sargassum has a very high reflectance in the near-infrared. And let's say to achieve finally an automated, efficient, and systematic classification, providing a high accuracy in satellite imagery, we utilized machine learning techniques and using a big data set as MARIDA. These techniques are commonly employed in addressing such a complex and somehow difficult task of classifying ocean feature with good accuracy or high accuracy, and considering that Sentinel-2 has 13 bands, we are actually using in our processing only in the end 11, but still is a lot of information, and so machine learning helps us to finally obtain let's say a trained model that we can use and apply to then classify a satellite image. So here I will. So this is our tool. It's available on GitHub, and you're really free to visit our page and clone our code and try it out. I didn't mention this. Our pipeline is all written currently in Python, but as Manuel later will explain, we also integrate some steps at the moment in Julia, and hopefully we will keep improving this part. So another motivation that driven us to let's say to make this available to everyone is open source is that nowadays at our knowledge automatic data pipeline with such a purpose we're still like rare in literature and yeah, so we make it open to everybody, and so that, let's say, we could foster the development of an operational tool for long-term monitoring of marine plastic in the ocean, but also other kind of features, as I explained before. So just to give you an overview, what actually is, so the pipeline. The first part, let's say, is the acquisition of the Sentinel-2 data that is done by defining a region of interest and the sensing period. And of course, it's needed also to have some credential to access the API services that we are using to download the data. In the beginning, we were using Sentinel-SAT package and downloading the image from the Copernicus Open Access Hub, but nowadays not more used. And sometimes was a bit difficult to download long-term archive data. So we decided to go for the Google Cloud repository where like the Sentinel-2 data are all available. Maybe they are not like ready available, let's say the next day, but it takes a bit longer, but it's quite good, let's say, way of downloading the data. But now we are actually using the most is the Copernicus data ecosystem, the space ecosystem, to download the data because as also was explained, I think, is nowadays what is mainly used, let's say. So the first step of the pre-processing before applying the classification is the atmospheric correction. So we download actually, didn't say, we're downloading Sentinel-2 level 1C data, that is top of atmosphere data, so top of atmosphere reflectances, and we want to remove, in this case, the Rayleigh scattering. So we obtain like an atmospheric corrected image of the bands, and we are doing this. We implemented this by using Acolyte package. There are several others, but in this case, we were, for example, it's possible to use also Send2Core, but we decided to use Acolyte because the dataset Merida that I showed before is also using the same, and we wanted to have somehow the same kind of course, reflectances somehow. Then there is a part like that allows to create the land and water masking. The land masking is made, of course, because we are not interested in classifying any pixel which is on land, on the coast, and we are creating the water mask using the ESA World Cover 2021. There's also an option for removing pure water pixels, depending on, let's say, a specified threshold by the user. And this can be done in two methods. One is by thresholding the band 8, and the other way is like by thresholding the normalized different water index, the NDWI. We also have an additional masking part in our pipeline, which allows to remove the clouds using S2 Cloudless, which is actually a method which is also used by Sentinel Hub in their platform, the one online, and allows, yes, to remove clouds. And even though our model is actually, our pipeline and model are classifying also clouds, since they are included into this Merida dataset, we decided to add also this additional option. So finally, once the satellite imagery are let's say, pre-processed, we can split it and then finally mosaic, and then we apply machine learning algorithm and models to finally have a classified image. The pipeline currently supports random forest and XGBoost models, decision tree models, but also we added an option to use pre-trained UNet models, so neural networks, and then Emmanuel will give you a bit of a demo and overview about the use of one of these models for the classification. So, well, I give the floor to my colleague now that will speak a bit more about the models, the one that we were working on, and give you a bit of demonstration about the tool.
Thank you, Andrea. Hello, everyone. So we tried a lot of machine learning models from Random Forest, XGBoost, UNet, and we also expand the library, the spectral signatures library, and we tested also on different places on the worldwide. One of the classes that we used to expand this spectral library was the phytoplankton blooms. We found quite a lot of challenges, especially when we are facing plastics and the contrast with plastics, foams, clouds, and ships, and it can appear a lot of false detections sometimes. And here, for example, you can check the scores for two models that we trained, and okay, they present a good score on the test dataset, but then when they go to the real world, it's a completely different situation. The integration of Julia into Python was from a collaboration from last year, Julia.io, thank you to Alexander, that used the Flux package to train and also develop the architecture of this UNet. And then at the AirCentre we integrated this Julia developed UNet model using the Julia call, Python call, which is really easy to integrate. And we have all explained the steps on our GitHub. And what was the main motivation behind this? First, to give more options to the user. Well, maybe the user likes to develop their machine learning models on Julia. Okay, put then this on Poseidon. So it gives the user more options, but also the Julia processing capabilities and the use of the GPU. Two applications of the Poseidon are the post-disaster management is one of them. For example, after flooding events, and here we tested on Honduras to detect pixels of the marine debris. And here you can see the small stars. They are clusters of at least 10 marine debris pixels that are on a distance of 100 meters. So this was a big flooding event. Honduras and South Africa, as I will show you, is very propice to this kind of events. So another application is for the long-term seasonal analysis. So we created a kind of a separated script for that we analyze several years of same area for the marine debris, and then we plot everything to see where is the clusters, maybe possible areas of aggregation that we can move the cleaning missions to those kind of places. And then we also compare this with the seasons, like the dryers and rainy season. So it's important to know that for us to expand this spectral library, for example, the spectral library to train the models, we always need the in situ validation. And in situ validation is a very hard thing on this kind of is a kind of a challenge, and we go to the newspapers, to the literature to find events, but also we use very high resolution satellite images from Geosat, since we have a partnership with them, but also regarding the La Plage, which is land-based solutions for plastics. It's a project, a Horizon 2020 project, which we are involved. We have the good thing that we have this the ship from our partner Alcor, where Andre was there, and he was able to find this bloom that was interesting to analyze. So improvements since the last July AO. Well, we were not stopped. We were not sleeping about this subject. We were working on this. And the first thing was the support for the new Copernicus data space ecosystem for downloading the Sentinel-2 products, which is working quite good now. But it's still on my GitHub. I didn't push to the AirCentre GitHub. I need to do that. And from also the collaboration for this UNet model in Julia to improve the GPU classification speed. And this integration, but also a web app prototype to show the Poseidon result. And this can be also like a challenge for you of how Julia can facilitate this web development, because this was a prototype, and this was created with Folium from Python. And this has some kind of limitation, especially on time sliders for several years. And when it goes to the mobile phone, it has a different behavior. So yeah, this is a thing that needs to be more explored. So the visualization and the analysis of the long-term data with the density and occurrency maps. This was for a project of regional interest, the EcoBlue, where we did this analysis for the Terceira Island, but also for other islands. And with this long-term analysis, we found that GeoTIFF may not be the most efficient way to store this data, because, for example, for the maskings, it is, occupying storage of 300 gigabytes. So this is, maybe we need to find an alternative for this, like the NetCDF or even different formats. And we trained, of course, new models and expanded the spectral library. So, yeah, I still have time. So I have a small hands-on session. It's really simple, and I will only show how the results look like that come from Poseidon. And the study case that I will use is this discharge event at the sea in South Africa from, 2 years ago, yeah. We are on 24 already. So as you can see, there is a lot of garbage, and how can you take a sun bath on these conditions? So it's important to move cleaning efforts to this kind of places, and Poseidon can help with that. So since Poseidon is quite big, the workflow is quite big, I will focus only on a small portion, like it will be the random forest and the visualization of this data. For this, I will use Docker, and also I will explain a bit where the data comes from. So for example, everyone has a different machine. I have a Mac, someone might have a Windows, another one call it Linux. So everyone might be have a different thing. So Docker allows to have a common environment to test this notebook without problems. The data, the Merida Random Forests model, it's a pre-trained model that we trained like some time ago with a recall of 91%. And this stack of data includes the 11 Sentinel-2 after atmospheric correction and 8 spectral indices. So let's go. Okay. So I don't know if someone tried to do the setup. I sent some instructions. Unfortunately, I don't have a lot of time, but I can also answer some questions if you have later. But the notebook is this one. It's here on the Julia 24. It's inside the notebooks. And then it's this Poseidon results demo. And here, you have a preview of the final, what you will be able to see at the end. And also there are two ways of doing this setup, the one of the Docker, which I recommend. And if you have already Anaconda installed on your computer, you can use this here on the bottom. So you have two ways of doing this setup. For the Docker, you only need to go to the Docker website, download Docker, you don't need the registration. After installation, well, you just go to, you need to make the clone of the repository, and you open a terminal inside this notebook that I will analyze right now, a PowerShell on Windows. And you just type this docker build t Poseidon results demo dot, and then this other command here. And this will start Jupyter. You also need to go to the OneDrive to do the download of the dataset. The dataset is 200 megabytes, I think, approximately. So it's a bit heavy. Again, this GeoTIFF thing, maybe with another format will be better. So I don't know if someone installed, if someone has a question, can make now some difficulties installing this. If not, I will continue here on the Jupyter notebook. So here I just do the import of some libraries. I want to give here some focus on the leaf map, which is the one that we will use to show the results. And oh yeah, and after you install the Docker and you set up the Jupyter, it will look like this. So the data will be inside here if you downloaded the data and replaced. And then you just put the path for the data. We read the data, and here you can see that it has the 11 bands and also some spectral indices like the NDVI, which is good to enhance the floating vegetation at the surface of the ocean. For example, to differentiate macroalgae. And then here is just initiating the leaf map, the map of in a certain location. In this case, it's the location for the South Africa. And here I add to this map a RGB layer, an NDWI layer, and the FDI layer. I select the color maps for this. You can also add a cell with M to see the status of the layers that are being added on the map, but I will do this, the visualization, only at the end. So for the random forest, for the machine learning training, I transformed all this stack into data frame. So this is mainly what is represented here. It's the machine learning features will be the bands and the indices, and the rows is like the values for, in the case of the bands, are the reflectances of the pixels extracted. Since the machine learning was, well, in here is to analyze the data. So if we have the stack that comes out from Poseidon, and we want to apply this pre-trained model on that stack, in this case transformed to data frame, it is transformed to data frame, to see where is the points of marine debris, where is the marine debris classification. Yeah, and the classification is done here. I also need to remove not the numbers. but at the same time I need to save this a structure of the data frame so that I don't lose geolocation. And I use this command here at the beginning because on the Jupyter Notebook it gives a strange bug, broken pipe bug. This doesn't work. This doesn't show on a normal script, but in Jupyter it shows up. And then I add this the classification. After it does the classification, I add this to the map with some. This is the colors. Like for example, marine debris is the one, and it will be in red. So this comes from Merida, the Merida dataset that Andrea presented. So the color status, it's all over there. And to also plot some points, some of the pixel center coordinates, I convert the geotiff to X, Y, and Z, but this is a very heavy file, so I convert it to a feather, which is more lighter. Probably there is a easy way to do this that doesn't need like converting the file and then saving on the machine and then converting again to the other one. And here is only a function that does this CRS, the conversion from the Sentinel-2 to the 4326. And to show, we only use the marine debris because it's the ones that matter to us. Yeah, after that we can just add this to the map, and the map will show like this. So this is in South Africa, you can see here. It's quite, yeah, but with this internet is quite hard. So it's supposed to show the base map behind. But this is the tile that we are analyzing, and you can see here some patches, some agglomerations of some kind of material. And after running this classification, it detects, well, some points that it thinks it's marine debris. There are also the other layers that we had. So this one is the RGB, but then there is the NDWI. And NDWI is quite good to find some filaments that can be at the surface of the ocean. And also the FDI, which is the floating debris index by Bierman et al. It's good for this kind of detections too, but it can have some kind of confusion with the clouds, for example, because you can see the filament has high values, but also the clouds in here has high values. So the confusion between the marine debris plastics, well, when I see marine debris here is the definition, well, it's here on the top. I put here the definitions for all the classes, and the marine debris is the floating plastics or other polymers mixed anthropogenic debris. And finally, the classification layer. I can remove this one. Yeah, okay. Yeah, and there is two kinds of reds here. There is the bright red, which is the marine debris, but then there is this darker red, which is natural organic material, like woods. And also we can see that it detects very well the clouds, but still there are some false, yeah, let me just remove here, just to see how well it detects the clouds. Yeah, it kind of detects well the clouds. And there is here, for example, a false detection, which he considers this agglomeration over here is a ship, which doesn't make any sense. And but this is a thing that needs more improvements. Yeah, so this was all I had to present it. I don't know, any questions?
I know it's way harder to make a data set for it, but have you considered using, again, SAR data, because it is possible to detect debris in SAR data?
What is the resolution?
Depending on
30 meters?
depending on what SAR image you use, you can have
The free one, Sentinel-1.
Yeah, 20 meters.
Yeah, 20 meters. Yeah, Sentinel-2 here, for example, the best one is the 10 meters resolution. There are papers that use SAR data for the detection of marine debris,
Yeah.
but the mainly literature about this topic is everything in Sentinel-2 based on the spectra of the materials. But yes, also SAR data is a approach.
But I mean, like I think the only real false positive you have for marine debris in SAR data would be sargassum or other similar algae.
But
Algae mainly.
yeah,
Otherwise, you don't have many bright features that looks like debris.
Yeah, but then I think this is correct. But I think we need an approach to that because, well, it's not just sargassum, but many other
Yeah.
things, especially in case of wind,
Yeah.
in the ocean, we can see out today from here, there's many white caps or like foams, like in the coastal areas, we have big difficulties in classifying and deciding if that is actually a good detection or not, because the foam that's creating from breaking waves,
Yeah.
that's like very bright and filament structure like thing, and maybe using optical data, we are a bit more like, let's say, more bands to play with.
Yeah.
While like SAR data, we have just single information, and then we are like, okay, we just have one. In the other case, we have 11. So that was the reason why. So of course, like SAR data does not problem with clouds. Amazing.
yeah.
But definitely something that could be integrated.
Yeah, I think there is a way to do this with different methodologies, but we can discuss later. When I look online on your data, it looks like the labels are points.
Yeah, pixels.
So it's like you labeled this pixel as being debris, or
Yeah.
did you? Because now it looks like there's actually like spatial structures. Did you do segmentation in the labels, or are the labels just points?
No, the labels are like coordinates.
Yeah.
And then like so it's extracting like the spectral signatures on all 13 bands
Yeah.
from that specific pixel. So it's annotated. So okay, this pixel is, we say, is well, marine debris or foam or ship,
Yeah.
and then give you like, so it actually was not made by us, the dataset. Maybe this is not what
Yeah,
it's not made by us. We use a dataset that's available. It was published in 2021, I think. So they annotated pixels and then
but
the bands.
That could explain the ships.
yeah, they don't annotate pixel by pixel. They create areas
Okay.
around, and then this extracts each pixel inside that area, the reflectance.
But they take the center of the pixel.
At least twice problem of big files. One of them was for masks.
Sorry?
You mentioned twice problems about the size of the memory consumption.
Yeah.
It was with the masks and the X, Y, Z points. The masks, you probably are using floating points. If you use shards, you can go no smaller than that in any, does not depend on the format. Are you using
Yeah.
or
No, I'm using, we are not using the float. We are using the uint. But then it's not, we are using int.
int? But
Yeah.
what size of int?
8.
8 bits, okay. You cannot go smaller than that.
It's
Yeah.
a binary mask. So
Yeah, okay. The other thing, the other one about the same type is XYZ. What I said in my comment is I see many types people using float 64, double precision, when you don't need that precision, that size of type at all. And that doesn't make a difference when you have small numbers, but when you have large number of files, data sets, normally float 32, which cuts by half, is more than enough for the things.
So if the Sentinel-2 comes in the float 32.
Sorry?
The Sentinel-2 data we are using is in float 32.
32, so okay.
Yeah.
I would better have been.
The problem is that about space and data storage is that the way that at the beginning we were working was like input, output, and for every step adding an input that was opening basically a TIFF file and then save it back to TIFF and then opening again. And so, of course, there is a lot of improvement we have to do, especially for this, and this is something we want to do, of course. But yeah, our main issue is that, basically.
Hello. I can shout. So my name is Guilherme Vaz, I'm from Blue Oasis, and we have been working with the ocean cleanup before, so you may know because it was the first company in the Netherlands that was cleaning the plastics. So one thing that can help you is that they have a lot of validation material, of course, so they know where are the plastics, not in general debris, but plastics. So I think once I made the contact with Pedro, with ocean cleanup, so if you are doing something, they are working on the same. So, but if you need like validation data where the plastics are, for instance, where they are working, possibly it's.
Wait. Let me tell this one. When I was talking also with them on this last event of Marine Litter on Netherlands, they were saying that they are focusing on the Pacific.
Yes.
Which is very far from the coast, right? And
Yes.
Sentinel-2 doesn't reach that area.
Well, then you solve the problem.
They use Planet's lab to data.
So another thing is that they, like them, we also did some work for them, and together with them, they are advanced, but on tracking plastics using cameras, not the same as you are doing. So with drones and with cameras on fixed posts and fixed things, because the plastic and the sea comes from the rivers. They're not most of them.
Yeah.
So, and for that we use like the problems you are having. Maybe you didn't face the problems. We are facing a lot of problems. Of course, the pre-processing is very important. So even more important than almost the machine learning algorithm. And so there's a lot of pre-processing we tried that we can tell you what we did, but it was for visual, not for these kind of things. And we use YOLO kind of architectures that was much better than, but it was for our case with images from drones and from cameras. So if you need to know something, Pedro has our contacts. We're still working with the ocean cleanup, so somehow can be some link with them if you want. Okay?
Very good idea. And when I joined a cruise ship like this last summer, we also had with the partners an idea of putting like cameras on the deck.
Yeah.
In order to instead of doing visual observation.
Yeah. We are trying to do that with the fishermen in Ericeira.
Yeah.
So if you have cameras on decks of fishermen or other people and you can detect the plastics, sends the data back home, and you know where the plastics are, then we have Lagrangian trackers to also check where the plastics are. Ocean Cleanup is working on that. We are trying to help a bit on that. But so to tell that there is a link here also if you want to talk with us afterwards.
Okay.
Yeah?
Yeah.
Okay.
Thank you again. Okay, so now we'll have a talk by Manuel Reintzler. Okay. Mr. Tiago Gomes and Guilherme Vaz about developing and applying MOHIT and Reef 3D models for scalable HPC. Manuel holds a MSc in Ship and Marine Technology from University of Rostock, Germany. During his industrial career, he worked mainly on aero and hydrodynamic analysis of floating renewable energy devices, aquaculture systems, and ships. He specialized in computational fluid dynamics, cable dynamics, mooring design, and scientific coding. In 2022, he started a PhD at Instituto Superior Técnico, working on numerical modeling of tidal energy resources and hydrokinetic turbines. More precisely, he is investigating new approaches to bridge the scale gap between regional ocean models and high-fidelity numerical tools enabled by high-performance computing methods. Computational performance, verification, and validation of the developed numeral models are key aspects of the ongoing research. For instance, he is simulating tidal currents in Tagus estuary using the open-source water modeling software MOHIT, running in parallel modes on multi-core clusters. Tiago Gomes is an aerospace engineering with the CFD specialization from Instituto Superior Técnico. His master thesis focused on the verification of moving grid methods for the CFD simulation of wind turbines. Since then, while at Blue Oasis, he has worked on various projects and published several papers in topics related to CFD applied to ocean sustainable solutions. Another one of his interests is underwater acoustics, having developed Raindrop, the new underwater noise propagation tool for Blue Oasis, capable of producing noise maps in real time. Moreover, he is currently working on a project to model the waves in the World Surfing Reserve of Ericeira, using the tool Reef 3D in a partnership with the developers of the code of NTNU. And Guilherme Vaz is an aerospace engineer from IST in Lisbon, with a PhD in offshore engineering, more specifically underwater acoustics, in the Netherlands. He spent 18 years in the Netherlands and was a research and development coordinator at Marine, one of the five big research institutes from the Netherlands, and invited lecturer at TU Delft before returning to Portugal in 2019. In 2021, he created Blue Oasis, a startup working on applied research and development for ocean sustainability, and he is now a research and development manager at this institution, visiting researcher at University of Southampton, and invited professor at University of Duisburg-Essen in Germany. His main expertise relevant for this conference is scientific code development and high-performance computing.
And with this text,
Thank
we don't need more presentation because, so let me see if this works. Okay, so good morning everybody. You know already everything about us. So my shoe size is 42 if you want to know. That's what she was telling. Okay, so we are going to present some... Vai buscar o nosso coisa. Yeah, I have mine also, so maybe it's, I don't know. I don't know, let's see. Doesn't work, we try ours. So, our scope today will be to present work that we have been doing with oceanographic modeling. Specifically two tools. One is the tool that Francisco already yesterday presented, is MOHIT, and another tool that we also developed. So, and you will see we don't use it, we are also developers of scientific codes, so I think we are also talking to the right choir. And it's Reef 3D, and all in the context of high performance computing. So everything we're doing here, it's not even a MacBook, it doesn't run in a MacBook. So we're talking about big supercomputers. So a little bit of background. So we are a startup in the mainland, in Ericeira. So it's the surf mecca of Portugal. If you like surfing and water, it's like Açores and Ericeira are good places. And we are all numerical modeling experts. So as you see, we brought a team of 3 aerospace engineers and 1 naval architecture. So in fact, we do most of our things in computers, and also experimental work. And we work on renewables, ocean cleaning, as you see in the previous presentation, is quite interesting. We also work in ocean cleaning, especially on not only plastics and debris, but also on acoustics. So noise is also pollution. Decarbonization, maritime and naval. So only offshore. Those are our main applications. We are all focused on offshore applications, use numerical modeling. So this is some examples of tools that we develop. So we are not only using tools that are out of the commercial tools, but mostly we develop our own tools. So those tools over there in bold are tools that we develop. So OpenFans is the tool that we developed together with Texas A&M in USA. Refresco was my tool in my PhD, or after my PhD at MARIN, Maritime Research Institute. It's like Deltaris, and most of you know Deltaris, so MARIN is as big as Deltaris in the Netherlands. And it's a CFD code that you will see a lot of applications here. I'll go into that. Raindrop, that is the tool from underwater acoustics, real-time noise maps that I think will be interested to merge. Those tools come from aerospace with the people using Earth observation and people more like on this context of this meeting. Reef 3D and MOET that we are going to show. So what you see over there, it's applications of computational fluid dynamics with one of the tools that we developed, Refresco. One is the fish impact on a tidal turbine. It's the one on the left. The fish come to the turbine. Of course, the fish are not stupid. They swim back. And that's the modeling of Lagrangian modeling of fish school with a turbine. On the right was the acoustics one. On the left you see a whale. So it's really the calculation of the flow around the whale. And on the bottom right is the modeling of ocean cleanup boom. Some part of the ocean cleanup boom, cleaning the plastics. So these are the things that are done with CFD tools, and CFD tools that our world, and we come from CFD into oceanographic, okay? So don't kick us, because we are aerospace engineers coming from the space to the water, and then from the smaller scales to the bigger scales. So CFD, we're talking about the smaller scales, the turbulent scales of things in the water. And we want to merge and go from the smaller scales into the bigger scales, where mostly here you're coming from the large scales going to the smaller scales. So post-processing, we heard a lot about post-processing. We do a lot of post-processing with tools like ParaView, that's some of you, or with Python, so far, with Python into ParaView, all batch processing in high-performance computing. And you see an examples of really calculations, but then rendered with Blender, so open source tool that can make movie-like realistic renderings of calculations. So this is not computer games, this is really calculations that we have done. And HPC, how can you do these things? So the calculation you saw over there for some part of the boom of ocean cleanup needs a supercomputer. We have a flexible structure. We have waves, we have plastics, so those things do not, those calculations, those codes solve the Navier-Stokes equations with a lot of models. They're not solvable in a normal laptop. We have like sometimes even more than 200 million cells, or even more, going to billions nowadays. You need high performance computing. So when I went to the Netherlands, already in 2002, I was using the SARA, so that's the supercomputer center in the Netherlands, and I started to work with Teras. It was a supercomputer with 4 cores. So, and since then we know that things speeded up, and so nowadays even our small startup, we have access to some HPC resources. So there's 4 clusters we are using around Europe. So on the left is our commercial cluster in Iceland. So it's called @North. And it's really a cluster. It's not cloud, it's not Amazon, it's really a cluster. It's ours, it's there. So it's our queue, we install everything we want, it's only used by us. It's quite, for a company, it's quite competitive. And as you can imagine, it doesn't need cooling in Iceland. and the electricity is also for free or very cheap. So on the right and bottom, so on the right bottom is a cluster that I together with Jan Albert, that's that guy over there, we mounted. So we developed that cluster. Is one of the biggest clusters in the Netherlands. It's at Maren, and we can use it only for research we do with them. But we have access also to IRIDIS and to clusters in Germany, and now together with Portugal FCCN. And Portugal will have a new supercomputer. It's called the Eucalion. It's in Braga, in mainland. And we are the beta testers of the Eucalion. And we would like to use MOID and Reef3D and Refresco, these three tools in the Eucalion, to show if the codes and software, because one main message today is that the code, the software and hardware in 2024 cannot be very much independent. I know that I've heard here people say you can run in GPUs and CPUs. It's a little bit more complicated than that. Sometimes you have to tune it and you have to do things independent for each hardware. It's not the same as programming something for a NVIDIA card or for Intel CPU or for ARM. So when we are using high-level languages, yes, maybe it's transparent for you, but for the guys like us that are doing the low level, not the same thing. So then it comes to the, what are we doing here together with AirCentre? So AirCentre teased us to, well, what are some of the tools that are available in Portugal for doing oceanographic modeling, and you guys know about small scale, so we can compute, for instance, the harbor here and see the waves coming into the harbor and the loads into the harbor or the wind into the building, whatever, these kind of small scales. But what about bigger scales? So we started to study oceanographic models, and we knew already MOID. So Manuel is doing a PhD on MOID. We knew people of MOID. We know one of the main developers, Camilo Neves. And because of our CFD, we know also the main developers of Reef3D. There's NTNU in Norway. It's Handbis and Vidar that we are doing projects together. So we are developing both these tools, not only applying, and seeing what are the pros and the cons. And that's our story today. We will show, Manuel will show things about MOID, Tiago will show things about Reef3D, pros and cons of all these two codes, where they fit in the oceanographic models, what are the pros and cons related with high-performance computing, and what are we going to do together with AirCentre to possibly make these tools into operational models and digital twinning. And now I pass the word to my colleagues, and at the end I will take some questions or even coffee break.
Okay, thanks, Guillermo. Okay, hello everyone. I am Manuel, and I have two disclaimers to make. The first one is also, unfortunately, no Julia in my presentation yet. Second disclaimer, I will talk about MOID, but I'm not even an expert user yet in MOID, like Francisco is. So this will be a little bit about our learning curve with MOID, what we have liked, and where hopefully in the future we can contribute with some improvements. So MOID, in general, you have already heard a little bit yesterday, is an open source water modeling system developed since quite a few decades already at the University of Lisbon, with a variety of applications. We have heard there is various flavors like water, land, Lagrangian. But here in this presentation, I'm also focusing on water, so on modeling estuarine and coastal hydrodynamics. And just an overview of all possible applications you can have. You see examples from the biogeochemical side, tsunamis, and also renewable energies. That is especially interesting for us at Blue Oasis. And here on the bottom right, tidal turbines, which is especially interesting for me because the tidal resource assessment, that is the subject of my PhD. So that is the first reason why I'm interested into MOID. A second one, why I'm interested into Mohit, is this question of scales that Guillermo already touched shortly. So my background is not at all oceanography, but I'm a mechanical engineer with experience in CFD. And CFD, we're rather on the side of the small scales. So we are looking at really high resolution models, but with the high resolution models, we usually can also cover only a limited domain size. And now CFD in an oceanographic environment, we have open boundaries of our domain. So we want to have realistic inflow conditions from the ocean. The problem is the models that are calculating those weather conditions, be it wind, waves, tidal currents, whatever, those are usually located on the other end of this scale bar at the large scales. Yeah? We have the global weather models or models spanning whole oceans. And the interesting part about Mohit is that it fits right into this gap. And it is lying in this, what we can call a mesoscale. So the idea of my PhD, in principle, is to take Mohit as an oceanographic code that takes input from global weather models and simulates coastal and estuarine hydrodynamics, and then later, long-term goal of the PhD in 2 years, using the output of Mohit as input for our high-resolution CFD models. You can see this is the CFD part is still grayed out. That is because that will be the future work. And for now, we are looking at Mohit and what we are learning with it so far. This is a quite technical slide on a numerical background of Mohit. I'll go very quickly through it. So it's a three-dimensional code. It has Eulerian, Lagrangian transport models. It has a turbulence model, spatial discretization, finite volume approach, thing that we are quite familiar with from CFD calculations. And then temporal discretization, we have here this semi-implicit ADI algorithm. And I'm stressing this now because you have to understand that Mohit development started already a longer time ago when computational resources, of course, were not that large yet, right? So this is rather computationally efficient and resource-saving code. But the development of this algorithm is already quite a few years back. And what that may have for implications for modern HPC applications, we will see in a bit. So now, how can we apply Mohit for HPC? Mohit is written in Fortran, which is a nice low-level fast code, so that is good. And we have various interfaces that we can use for parallelization. We have already heard MPI in some of the presentations, and there's also a second interface, OpenMP. Here in this presentation, I will also be focusing on parallelization with MPI. So now, what have we done at Blue Oasis so far? Now, at the beginning, we thought, oh, great, it's an open source code. We can just go to GitHub and download it. But then the first obstacle that for new users you will quickly find there is no open source graphical user interface to it. There has been a graphical user interface for it, but it was sold to a software company. And so now today it's proprietary and we cannot use it anymore. That means for pre and post-processing, we are more or less on our own or on the existing scripts that already exist. Just an overview, I mean, bathymetry, you can get it from EmodNet, downloading it, everybody can do that. But then, what do you do with the bathymetry data? You need to cut it, you can combine different bathymetry files, You need to interpolate it, you need to implement the land, you need to export it to the files that Mohit actually understands. And all of this in the beginning was a big obstacle for us, and so what we did, we contracted a very good master student for us, and his task was exclusively to help us get going with this Mohit and developing a few scripts so that we can more professionally apply a Mohit. So everywhere you see here this blue marker, that is where we have developed some scripts, mostly in Python, maybe in future in Julia, who knows. And yeah, we have pre-processing tools. We have all about bathymetry, then domain decomposition that we need to distribute different parts of the domain for the different processors. We need to interpolate also the input files from the meteorological models. Also, therefore, we have developed, or our student has developed a script. And then post-processing, the output of Mohit, you need to convert it so that actually our post-processors like ParaView and TechPlot can read it. And Francisco has already spoken a little bit yesterday about it, that usually like in ParaView, but also in TechPlot, it's quite cumbersome to treat with this data. Yeah, you have to do a lot of clicks. So there also our approach is we take the programming interface with Python and write a few scripts, so that saves us in the end, after we repeat always the same operations, it saves us some time and we don't need always to do so much clicks. Another thing we did with Mohit, and actually also RefraD, we containerized it in Docker that we just heard. If you have already compiled a code from GitHub or a source code yourself, you know it can be a bit hassle. Either packages are missing, or then you're switching to a different system, and then the compilers are not there. So all this mess, we want to facilitate it a little bit, so we packed it into Docker, which is basically providing a virtual environment to be able to run Mohit then with all the packages and compilers already there, and the only thing that you need to do is actually install Docker and load the images. And that is working for us, and we've tested it on all 3 platforms, and that is working nicely. But now for some applications in the end, and we will be here looking at the Tegus model, which was my first contact with Mohit. So why is the Tegus interesting for us? So in the Tegus, we have currents coming from the river and several sewage systems. We have the tides that push in water, and then the water flows out again at low tide. And we have here this narrow river mouth, which basically accelerates the flow. Next to the Tejo River, we have Lisbon as a thriving urban city, and of course, in today's world, we are always looking for new sustainable energy generation sources. So all these things combined lead to our assumption: hey, could in the Tegus River, in this thin river mouth, could that not be a nice application for tidal turbines? And that is what we are going to check. And if you want to know if it is suitable to install tidal turbines, the first thing that you will do is a resource assessment. So you're basically simulating and checking what are the current speeds that we have there, and at which location would be nice to install our tidal turbine. Now, we are not the first ones simulating the Tegus model. Actually, Martech at Lisbon University, they have done it for a long time. But so far, the existing operational estuary model has a resolution of around 200 meters. And if you see that, with respect to the size of a tidal turbine, which I think the largest tidal turbines today, they have a diameter of 20 meters. Yeah, there's still a big gap between those 200 meters resolution and a 20-meter tidal turbine. So there's a lot of flow information that may get lost. On the other hand, we have higher resolution bathymetry data for this narrow river mouth available. They're freely downloadable on EMODnet. So there we have resolutions down to around 11 meters. So if we can get a numerical model that of this Tagus mouth that we manage to scale down in resolution, this would already be much better for us for tidal energy application. So here is our setup of the Tagus model. I'm also not going too much in the technical details, but maybe more looking at the table that you see there in the bottom, because there is the already existing 200-meter model, and what we did is we tried to refine the mesh 2 times, going down in resolution to 70 meters and even 25 meters. And what that does, of course, the number of cells is exploding. Yeah? From 3 million cells in the beginning, we are going suddenly to way over 100 million cells. And if you start simulating, you will also see that the computational resources then, of course, are much larger. That consists RAM usage, but also computational time. And for example, here the computational times in the last in the last row, they are for 1 core for a 24-hour simulation, so covering like two tidal cycles. And you see that the 200-meter model simulation time of 3 hours, 1 core. Yeah, you could still run that on a on a laptop almost. Yeah. 70-meter model, we already have the simulation time of 1 day. So it would still be possible on a desktop without question. Then if we go to the 25 meters, we are suddenly reaching a simulation time of a month. Yeah, we're not going to put this simulation on a single core and wait for 1 month for our result, and maybe then noticing that we did a mistake and we need to run all over again. So this is where parallelization comes in, and also actually becomes necessary to make it usable in a professional environment. But enough of technical details so far. I'll just show you like a quick video of what a result or an output of such a hydrodynamic simulation may look like. And yeah, we see here current speeds in the river estuary combined with the tidal effects. We can see here at the borders of the river some intertidal areas that fall dry and dynamically wetting. And we can see a transect of the river with the current speed. And this was created by our student, and a lot of this data was actually then extracted and put in our post-processor with the Python script. So then we don't have to set up every time everything by hand again. But now the question, well, how good are the results that we are getting out of this model? So what we usually are looking forward to is experiments trying to check our flow data that we have simulated. Problem that for this Tagus area, it's really difficult and almost non-existing to find up-to-date experimental data. So what we did was to construct our own low-cost campaign with some GPS drifters that we made. It was basically just a buoy with an underwater sail equipped with a GPS locator. And we packed a few of them on a small boat, sailed out into the river, 3 different locations, measuring a few times on 2 different days, and yeah, creating our own experimental data. And here a little bit the overview of the results that we got out of it. Positive thing, we have observed current speeds well above 1 meter per second in all 3 sites. Of course, varying a little bit depending on tidal situation. A problem or a challenge, we have a relatively high error of 30% in those measurements. The reasons or possible reasons for that, they are discussed in the paper that I can send you if you are interested in that. I will not discuss it here in detail. But what I want to bring your attention to is here the graph on the right. And there we are comparing actually the 200 meter model with a 70 meter model. So 2 models with different resolutions. 25 meter resolution model, I have unfortunately to say, it's not running stable yet. We had big difficulties with this low resolution model. But here the comparison between 70 meter and 200 meter models, and you can see that the thick line tends to fit the experimental data better than the Corsa model. It's not super obvious, but the trend is definitely there. And this is, of course, a motivation for us that sees, yeah, actually high resolution for our tidal research is actually, yeah, a thing, and we need to push further to get to these higher resolutions. But now, where we also want to push is, well, the technical part behind it, the parallelization. You have seen for for high resolutions, we need parallelization. So what we did is a scaling study. Essentially, what the idea is, you hope if you use 2 cores instead of 1, your program would run twice as fast. If you use 4 cores, it runs, or you only have a quarter of simulation time. Of course, this is only the ideal behavior, and in a real-time world, you always have an overhead, so nothing is ideal. But we tried a scaling study, so we used up to 40 cores, and we're measuring computational time and then checking out the performance. And we did that even with different domain decompositions. The standard domain decomposition in Mohit is lines. So you basically take your big domain and you cut it in lines. And then those small lines are calculated separately on each processor. But we manually also generated other domain decompositions. For example, here the regular sized rectangles, which is quite more typical in CFD than just using lines. And then also another optimized rectangles in order to distribute the water points that are the most important for our calculations equally across all subdomains. And here are the results, and the results, they are, we were not really happy with it, because you can see the ideal behavior would be that diagonal line, and all 3 domain decompositions, they are quite far from it. So the overhead that we are getting is a lot, and we are diverging very quickly for a high number of cores from the ideal speed up. Not only that, also it seems that with the growing number of cores, our simulations are getting more unstable. And we think that the problem is actually the solving infrastructure. You know, that was developed already like decades ago, not necessarily in mind with the highly parallelized hardware that we have today. But there is new solving procedures that exist today and that are successfully working in CFD. So we hope that with our CFD background, we can actually improve maybe the solver and getting a bit closer to, or getting a better scaling performance out of Mehit to make it fit for modern HPC applications. So, but now, I mean, you may think you local people, here's a guy coming from the continent only talking about Lisbon, the capital, and the Tagus. So I also wanted to show you a local example, like Francisco has done, Azores model. We are here on the easternmost island on the south coast, but what we will be looking at here is the channel on the left, the small channel between Pico Island and Fayal. And you see this example is radically different from the Tagus model because we don't have flat intertidal areas, but we have huge water depths and open boundaries all around the islands. Problem is, bathymetry is highly variable along this boundary. It's basically impossible to have a smooth bathymetry at the boundaries, which is kind of required for Mehit and which can lead to instabilities, which we were also observing. Resolution for the model will be around 100 meters. So for the large domain that you have seen, only in the horizontal we are reaching 4.4 million cells with this 100-meter resolution. We were forcing tides, we were using a turbulence model, and then inside the channel we were placing 8 gauges, so 8 measurement stations basically to analyze the currents that we observed there. And then, yeah, I just for learning purpose, I used a lot of different settings. I will not go through that exactly. It was not only out of interest that I used all those different setups. It was kind of forced a little bit because the 3D model was also not running stable. And until today, I did not manage to get it running stable for like for a full day of simulation. So usually after a few hours, we always have some divergence. And we assume that it is due to the highly variable bathymetry data. So I will have to work a little bit more on that, taking a little bit coarser resolution at the boundaries or just applying some smoothing. But another interesting part here, comparison of 2D and 3D model, we can still take some runtime estimations. Just by adding a few vertical layers, we get a lot higher number of cells. Again, for the 3D model, we would need higher amount of memory. And of course, also our computational time rises. And the thing is that the parameters that you see here, these are already for simulations running on 10 cores. So this is already parallelized, and 10 cores, maybe you can still run it on a desktop, but laptop, definitely not anymore. And if we want to push this model for even higher resolutions, then you can definitely imagine that this will also require HPC resources. Here a short video about the 2D model that was running fine, and you can see here the velocity vectors, little bit of circular motion of the tidal flow. Can also look more detail in the tidal channel. You can see a little bit the flow direction from the flow detachment that you can see from the small islands or the protrusions of the bathymetry. And the maximum current speed that we observed was around 1.4 meters. So yeah, it's getting quite hefty, and you will definitely notice if you're out there with a boat. But now, what does the measurement stations, our tidal gauges, give that we put there? Water level is a variation, is a little bit noisy, but it's what you would expect, a sinusoidal shape. And it oscillates around 1 meter with an amplitude of around 600 meters. But velocity magnitude looks a little bit chaotic, doesn't look regular at all, right? So what is the reasons for that? And then you can split up the velocity component between north-south and east-west component. And then you can see, finally the vertical velocity that we have on the left, that is quite a bit more regular. So the flow going up and down inside the channel. But we have this horizontal component that does not necessarily work consistent on a 12-hour schedule, but messes a little bit up with the irregular shape. So these are resolutions that you can pull out of these models. I will come to the end to leave a bit of time to my colleague. So what have we liked about Mohit? It is open source, it is modular, we can extend it with our own applications. It has already a wide application range, so there is tons of models already existing that you can use and imitate. And we have friendly developers. I only need to go over to the next building in university, and I'm speaking directly with the professor. Challenges: no graphical user interface, the poor scaling performance on HPC. We have seen like getting really to small scales has its limits. But we want to work on that. So short-term plans are improving the solver, so removing maybe these instabilities that come on these high-resolution models and make Mohit fit for large-scale HPC applications. Running verification study when we can run the small scales. We can do a grid refinement study and estimate the numerical uncertainty of our simulations. And we want to keep improving and standardize our pre- and post-processing scripts. And that is maybe even where Julia may come in the future for the post-processing. I've already seen promising stuff. Long-term plans for my PhD, coupling with CFD, or maybe even implementing sensor data from the real world and putting that into the numerical model and exchanging data. It's word digital twinning is in every mouth. But those are dreams for the future. So far, I'll stop here and leave the last 15 minutes, I hope that's enough, for my colleague that will talk now about Reef3D, which is more recent code than Mohit, and more specialized on waves, which we have a lot of today outside, so I think it's very suitable. Please.
Good morning, my name is Tiago, and thank you, Manuel. So right now, as Manuel already mentioned, I will be talking a little bit about Reef3D and wave models here in Azores. So as we already introduced in the beginning, Reef3D is an open source aerodynamic framework developed at NTNU. It's completely open source, you can find it on GitHub, and it's actively developed. Every few months there's new releases with new features, and it has a growing user community. And it's a framework because it consists of 4 tools that you can see here. So on the left we have Reef3D FNPF, which stands for Fully Nonlinear Potential Flow, and will be the focus of today's presentation. It's really good to model large-scale phase-resolved sea states, and you can see an example there that's available on the website of wave propagation in the Norwegian fjord. Then we have Reef3D S-Flow. This is a 2D case, a 2D solver, because it solves the depth average, non-hydrostatic shallow water equations. It's more adequate for river flows, open channel flows, and it has models for sediment transportation. And we also have the newest addition to the lineup, Reef3D NH Flow, which solves instead the non-hydrostatic Navier-Stokes equations. In relation with FNPF, it has the advantage because it can capture dynamic wet and drying at the shore, and it's just being finalized at the moment. And then what may be the most familiar based on the name RIF3D CFD, which resolves the full Navier-Stokes equations with turbulence models and a level set 2 equation phases. Also includes high fidelity physical models, like the possibility of modeling 6 degrees of freedom floating bodies, moorings, nets, which is really handy if you want to model, let's say, an aquaculture cage, as you can see there. Overall, what might be the most similar one to MOHID in this case is really NH-flow because of theoretical background, but of course in this case RIF3D is specialized in waves. RIF3D has been developed also having HPC in mind, and it's fully modularized C++ code, and we use that at Blue Oasis in our clusters. So today, simulations were all run in our cluster in Iceland at North, and I will be presenting it here. And to showcase that HPC suitability, you can see here some strong scaling studies that were performed by the developers. So we have RIF3D, CFD, and S-Flow, and in all cases, the speed up with the increasing number of cores is very satisfactory. While they have not been officially benchmarked yet, FNPF and NH-Flow share the same HPC framework, so we should see similar results to it. Another great advantage of RIF3D is the capability of bridging the scales, like we were discussing up until now. So this is just an example of a potential workflow. Of course, there are others possible. But we can start even with external tools like SWAN, which work on, some of you may already know, and they are frequency-based. And they model waves using the spectral action balance equation. They are really efficient and work really great at large scales. Then we can couple that with RIF3D FNPF because we can receive wave spectra as input boundary conditions. And in this case, we solve the waves in a phase-resolved fashion. And this was a study done by the developers of RIF3D. Compared with SWAN, FNPF is able to capture nonlinear effects like diffraction and reflection, which SWAN struggles with. And by having these C states that are really useful, for example, 3-hour C states, they are really common in coastal engineering, we can do something that is very rare to find, which is to couple directly with a CFD solver. And that way we can, for example, get a realistic C state to model and to simulate the impact that it has on offshore structures, like, for example, aquaculture or wind turbines. In this case, as I already mentioned, our focus in this presentation will be the FNPF model for Azores. You can see here the domains that we created. So this is already the grid generated, including the islands of Fayal and Pico. And we have 2 domains. So one large one encompassing all of the islands, which has around 60 kilometers by 35, and then a smaller domain in the channel. Note that all the bathymetry data was retrieved from eModNet. In terms of wave conditions, I have simulated 2 for this particular workshop. So the first was based on data that I could find during a day in November 2023 in IPMA. IPMA runs these frequency-based models like SWAN or WAM. And in that case, in that particular day, for the central group, the significant wave height was around 4 meters in that it had a peak period of 12 seconds, with waves coming from north to south. And in the second case, I wanted to have a more realistic extreme event. And in that case, I picked Hurricane Lorenzo, which passed really nearby Azores back in October 2019. It was a Category 5 hurricane. And if I recall correctly, it was also the one that progressed further east in the ocean. In this case, the significant wave height was around 10 meters, based on recordings that I could find, and it had a peak period of 13 seconds, with waves incoming from southwest to northeast. In terms of wave modeling, I have used first-order irregular waves, and they are described based on a ion swap spectrum. Once again, we can pick this information from SWAN, let's say. And I have added some directional spreading to add some irregularity to the sea state. And here is a snapshot after 4 hours of simulations for the larger domain with the 2 wave conditions. So in total, 4 hours were simulated. The first to let waves propagate and let the transient effects dissipate, and the last 3 to get the 3-hour sea state. In this case, the grid generated had a 40-meter cell size, so we are talking about 13 million cells, and with 96 cores, it took 22 hours to complete the simulation. So we have a ratio of around 5 hours of computational time to simulate 1 hour of real time. And the RAM usage peaked at around 18 gigabytes, so around 1.3 gigabytes per million cells. Rift3D has also the capability of doing some post-processing during the calculation. For example, we can see here the average of the last 3 hours of simulation. And in this case, we are plotting the significant wave height. It's clear to see here the shade effects created by the islands and also the strong diffraction effects that some of the coastline introduced in the waves. And if we go to the smaller domain, the second one, so around the channel, here in this case, we refine the grid. It has only 10-meter cell size, and the total number of cells is 12 million. Running with the same node at north, the computational time increased to 48 hours, because in this case, we need to maintain the Courant number equal to unity, and since we have a smaller cell size, we have a smaller time step. Therefore, more iterations are needed, and the RAM usage peaked at around 16 gigabytes. So once again, 1.3 gigabytes per million cells. And to illustrate, we have here a video. I really decided to show the first, if it plays. We have a video of the waves propagating in the channel. This is really the first time steps of the simulation. I think it's more illustrative in how the waves start to interact and also how Rift3D works. I just want to point out the diffraction effects that you can see, for example, in Monte da Guia and Porto Ping here in Faial, and also in Porto da Madalena in Pico Island. These ilhéus here, they create a really strong interaction, diffraction, and the waves that are going from towards the north-east direction are redirected really in front to southeast towards the port of Madalena. So this is really interesting data. And of course, we can also get some significant wave height plots during the simulation. Another possibility is also we can include wave gauges. So these work as if we have buoys spread out in the domain. So we can see here, once again, the channel between Faial and Pico Islands. The gauges were placed really along the path that is taken by the blue line, so the ferry between Porto da Horta and Madalena in Pico. And we can expect that a ship leaving Horta will have a smooth ride at the beginning, but as soon as it starts arriving at Madalena port, it will start to become a little bit bumpy because of some wave construction effects when the waves are incoming from the north. On the right, we have some post-processing of the wave gauges. We have the wave height, which is then post-processed in some relevant oceanographic parameters. We have the zero crossing significant wave height, which is calculate all the wave heights, sort them, and calculate the average of the highest 1/3 of the waves. Or we can calculate also based on the spectral moment of the data, which is what Rift3D do. And of course, in this case, I have used Python, but we could use Julia. And I believe, based on what I've seen in this workshop, we could really profit from handling large data sets and making some nice visualizations of the data. And of course, we also have here the typical wave spectrum that we can extract. We are not only applying Rift3D in Azores, we also apply it in Ericeira, so where we are based. This is a project that we are working together with NTNU, so the developers of Rift3D. And the goal here is really to model the surfing waves in the reserve, which nowadays the information available for surfers is really insufficient in terms of wave forecast, and we believe that Rift3D could create some really good operational models with really good insights for surf. In terms of outlook, at Blow Oasis, we want to continue maturing the tool coupling, so not only with external tools, but also within Rift3D to develop operational models targeting digital twins, and to continue contributing to Rift3D and also start putting our contributions in the official repository of Rift3D, taking advantage of our team's experience in numerical tool development. For Rift3D, the future also looks bright. They recently have been awarded an European Research Council grant for particle resolving segment fluid interaction, which in my opinion, will bring new features to Rift3D, including currents, which will expand also its oceanographic features. Also, just to finalize now the presentation, in terms of oceanography tools and HPC, of course, these tools have been mostly based in low-level languages, which are very efficient, like Fortran, C, C++. For post-processing and pre-processing, maybe Python because of its ease of use, but I think Julia here could also make a difference in automatizing these workflows. and for both pre and post processing. Also, we have seen that these traditional tools have some poor infrastructure. Some of times they don't have clear verification and validation infrastructures, or even clear also best practices of DevOps. And we believe that this is critical if we want to have mature codes that can be used in a day-to-day and operational model context. There are also new HPC challenges in the horizon. The first one being the increase of ARM CPU architectures. As Guilherme mentioned, we have the Ocalian in Portugal that's opening this year, if I recall correctly. Some codes may be better prepared than others to make this transition. And if we talk about exascale computing with new heterogeneous architectures, merging CPU and GPU resources, this is already other types of talking, and some of the codes may not be suitable and may to be fully rewritten to handle that. At Blue Oasis, we also work with artificial intelligence, and we believe that these AI models can bring some value in also these operational models of oceanographic tools to speed up the simulations to be running constantly 24 hours, 7 days per week. So with this, I wrap up my presentation, our presentation. Thank you for your attention, and we are open for questions.
Just some comment for one question that we can, I think we can also help you with some of the timing, but of some of the applications, and that would be, and we are very welcoming your contributions to improving the improvement of the code for making it faster. And I also very surprised, as well, another comment on the validation with your homemade system. So I think that the model is working quite well because it validates with this technology. I think it's doing a good work. But also sometimes I think that you could consider is not running, of course. If you have all the computing power, you can do a lot of all the domain. But sometimes you can do a small domain. And now the model is able to do two-way nesting.
Yes.
So whatever you change in a small part of the model, you can bring to the greater model that doesn't need to have this. Had you tried this? Or?
Yeah, so with the nested models, what we have encountered as problem is when we want to go to parallelization. Because if you have a nested model, from our experience, you only can parallelize the smallest model that you have into the domain. So MPI is not able, so you can only apply MPI to the smallest model and not to the parent models then. So you could reach at some point, if you have like several steps down with the nested models, that your very coarse but large model is slowing down maybe the small part in the middle. Also, it is a bit of tricky because there are limitations with the nested models. You know that you have to fit like the grid spacing so that it coincides with the coarser grid lines, right? And you need the time steps to be multiples or fractions of the coarser model. So there are some limitations that parallelization would have with nested models. So that is why so far we haven't considered that. Maybe now for the Azores case, where I've told you that with the high resolution models, I have difficulties with instability. There maybe it could be an idea to make maybe a nested model with one coarse domain, which doesn't have which is much smoother at the boundaries and maybe wouldn't have the same instabilities that we have with the high resolution model. But yeah, we've been distancing a little bit so far from that because of the limitations it brings to MPI. But yeah, I mean, we just have started, so that is something that we need to look at in the future.
We can discuss that.
Yeah.
We can help.
Sure. Great. Thanks.
Make it short then. I never used Mohit, but I used another model, ROMS, which I guess is similar. So it's also a terrain following coordinate model. And typically when you use a bathymetry, you have to smooth it, and there are some theoretical results, theoretical thresholds that you should not increase. So when you mentioned the instability, did you use the bathymetry as it is, just interpolate it on your model grid, or did you already apply some smoothing?
Yes, in this case, it really was like it is. It was like the 100-meter resolution that is coming out of it. So that's why I also concluded that probably this is the problem. Yeah.
Yeah.
Okay. Okay, so that's why. So Reef 3D is completely different code. It's finite volume and you can answer. So did you do some smoothing?
Yes, with 3D automatically has included in the grid generation smoothing iterations that the user can...
So we don't have to do anything, so you adapt...
Yes, but I try to keep them low because otherwise we start losing some features of the coastline and bathymetric features, but there's some smoothing included.
So if there are no more questions, I'd just like to give a bit of context. The AirCentre, for this work that was just shown here, the AirCentre aims to have operational models for the ocean. We need to scale, and we need them in operations, which is not the same as just doing research. And so we asked Blue Oasis for help with understanding the limitations, and it was good to see the limitations. So sometimes you just don't throw more computing power at things. It doesn't make sense. It doesn't work like that. So it was great to see this. Thank you very much. And also a note: we're not limiting ourselves to these particular models that were shown here today. We want to explore other options too. So we're in this moment now, in the next few months, years, exploring these as much as possible. So any suggestions, if you are in the room or if you are online, please, we're happy to hear you. Before I pass the microphone to Simon, since I have it now here, just an announcement for all of us now. Before going to lunch, could we have a group picture? Because the weather is not, we hope to do one outside, but better have, better do one now. And then if weather gets better, we can always repeat. Simon.
Great talk and very interesting with the models, and also, but for some of the applications that you presented, have you also considered doing a data simulation for the model and like simulate observations continuously or input from the weather forecast or like weather nowcasting to correct the model predictions in each step?
I mean, that would be the future. That is what we've put in there a little bit with the idea of that digital twins or operational models. And actually, for the Tagus River from Martech site at university, you already have an operational model for the Tagus. Or not only for the Tagus, but for the whole Portuguese coastline. So if you're interested in seeing that, I can give you the link. And there they really take, I think it's GFS or WRF weather model output, and then make a nested domain approach the Portuguese coast, and then scale it down by steps. So these operational models that already exists.
Thank you.
But it doesn't exist yet with sensor data, with live sensor data. So that would be the big step ahead now. Okay, then thank you. Then let's do a picture. The sun is shining.
Just a quick note for those who are online, we'll now have the lunch break and we'll be back at 1. Thank you.
Maybe we could do a like a giant wave behind. Splash.
Question is the model differentiable?
Yeah.
Why can't you beta simulate?
That's rule 1.
No, I mean there's also like grade 3 simulation methods, right? Yeah, there are some really interesting ones, but I don't think they're as efficient.
Yeah. I mean, I'm not a simulation expert, but
I'm not quite sure whether these areas want to talk about these like gradient free methods because their model is differentiable, or like let's say it this way.
yeah.
It's actually not differentiable. They just hand code
The gradient makes us.
Não, eu ainda estava aqui a fechar só com a Catarina.